There is a new player up there, and this player is the strongest one yet. When I say up there, I mean the space, and I know you cannot guess. So let me tell you, I'm talking about the James Webb Space Telescope, or JWST, is a space telescope that focuses on infrared astronomy. The most powerful telescope ever sent into space, its substantially improved infrared resolution and sensitivity will allow it to see things that the Hubble Space Telescope can't see because they're too ancient, far, or faint. This is projected to open up a wide range of astronomical and cosmological inquiries, including views of the earliest stars and the birth of the first galaxies and thorough atmospheric characterization of possibly habitable exoplanets. JWST was launched in December 2021 from Kourou, French Guiana on an ESA Ariane 5 rocket and is still being tested and aligned as of May 2022. JWST will follow Hubble as NASA's premier astrophysics mission once it's operational, scheduled around the end of June 2022. The James Webb Space Telescope's mass is roughly half that of the Hubble Space Telescope. The JWST's primary mirror comprises 18 independent hexagonal mirrors with a diameter of 6.5 meters. The polished area of the mirror is 26.3 meters, with the secondary support struts obscuring 0.9 meters for a total collecting area of 25.4 meters. The collecting area of Hubble's 2.4 meter diameter mirror, which has a collecting area of 4 meters, is more than 6 times greater. A gold coating provides infrared reflectivity and endurance to the mirror. JWST is primarily built for near-infrared technology, although depending on the instrument, it can see the orange and red visible light in the mid-infrared spectrum. It can detect things 100 times fainter than Hubble and objects from much earlier in the universe's history, as far back as redshift Z20, about 180 million years cosmic time after the Big Bang. For context, the first stars are thought to have formed between Z30 and Z20, about 100 to 180 million years cosmic time, and the first galaxies around Z15, about 270 million years cosmic time. Hubble can only see back to the very early stages of reionization at roughly Z11.1. The design prioritizes the near to mid-infrared for 3 reasons. The visible rays of high redshift, very early and distant objects have been shifted into the infrared, and their light can only be observed today via infrared astronomy. Cooler objects such as debris disks and planets emit the most infrared radiation. These infrared wavelengths are challenging to study from the Earth or with existing space telescopes like Hubble. The Earth's atmosphere, which is opaque in many infrared bands, must be viewed through ground-based telescopes. Many of the target chemical constituents, including H2O, water, CO2, and methane, remain in the atmosphere even when the atmosphere is transparent, highly affecting research. Existing space telescopes like Hubble are unable to investigate these bands because their mirrors are too hot. The Hubble mirrors are kept at around 15 degrees Celsius, and the telescope itself radiates heavily in the infrared bands. JWST may also examine nearby objects with an apparent angular rate of motion of 0.030 arcseconds per second or less, including entities in the solar system. This includes nearly all known Kuiper Belt objects and all planets and satellites, comets, and asteroids beyond Earth's orbit. It may also observe opportunistic and unplanned targets like supernova and gamma-ray bursts within 48 hours of deciding to do so. The James Webb Space Telescope has completed a grueling series of phases that'll soon allow humankind to see deeper into the universe than they have ever seen before. The most powerful telescope ever launched into space has made it through the most dangerous stage of its mission, a perilous deployment comprising hundreds of life-or-death maneuvers. There are currently no spacecraft capable of reaching Webb at altitude to repair or refuel this space telescope. NASA spent so much effort building and testing Webb to ensure it could survive alone in the dark for an extended period of time. The pointing flexibility of the James Webb Space Telescope is smaller than that of the Hubble Space Telescope. Because the telescope must face away from the sun to keep its instruments cool, its field of sight will cover 40% of the sky on any given day, and accessing the entire sky will take about 6 months. JWST is in a halo orbit around the Sun-Earth L2 Lagrange point, about 1,500,000 kilometers beyond Earth's orbit around the Sun. Its natural position varies between 250,000 kilometers and 832,000 kilometers, or 517,000 miles, keeping it out of both the Earth's and Moon's shadows. Hubble circles 550 kilometers, or 340 miles above Earth's surface, whereas the Moon is around 400,000 kilometers, or 250,000 miles away. Objects close to the Sun-Earth LT point can orbit the Sun in synchrony with the Earth, allowing the telescope to maintain a reasonably constant distance while maintaining its unique sun shield and equipment bus orientation toward the Sun, Earth, and Moon. With its wide shadow-avoiding orbit, the telescope can block incoming heat and light from all three bodies simultaneously, avoiding even the tiniest temperature changes from Earth and Moon shadows that would affect the structure while still maintaining solar power and Earth communications on its sun-facing side. This method keeps the spacecraft's temperature consistent and below 50 K, required for feeble infrared measurements. NIRCam or near-infrared camera is an infrared imager with a spectrum coverage ranging from the visible edge, which is 0.6 meters, to near-infrared, which is 5 meters. There are 10 sensors, each with a 4-megapixel resolution. The observatory's wavefront sensor, which is necessary for wavefront sensing and control operations, will also be utilized to align and focus the primary mirror segments NIRCam. The near-spec or near-infrared spectrograph will also conduct spectroscopy in the same wavelength range. The European Space Agency manufactured it as Aztec in Noordwijk, Netherlands. Members of the top development team come from Airbus Defence and Space in Ottobrunn and Friedrichshafen, Germany, and the Goddard Space Flight Center with near-spec project scientist Pierre Ferruet. 3 observation modes are available with the near-spec design: a low-resolution prism mode, an R1000 multi-object mode, and an R2700 integral field unit or long-slit spectroscopy mode. The methods are switched by operating the filter reel assembly, which selects a corresponding dispersive element, and the grating wheel assembly, which selects a corresponding dispersive element. Both mechanisms are based on the Infrared Space Observatory's successful isopod wheel mechanics. To allow for simultaneous observations of hundreds of separate objects everywhere in near-spec's field of view, the multi-object mode uses a complicated micro-shutter system. Each sensor has a resolution of 4 megapixels. Carl Zeiss Optronics GmbH, now Hensoldt, of Oberkochen, Germany, was contracted by ASTRONOMICAL to develop, integrate, and test the mechanisms and their optical parts. MIRI, or mid-infrared instrument, will measure wavelengths in the mid to long infrared region of 5 to 27 meters. A mid-infrared camera and an imaging spectrometer are both included. MIRI uses wheel mechanisms identical to those used in NIRSPEC, developed and constructed under contract by Carl Zeiss Optronics GmbH for the Max Planck Institute for Astronomy in Heidelberg, Germany. Mid-2012 saw the delivery of MIRI's completed optical bench assembly to Goddard Space Flight Center for ultimate integration with the ISIM. The temperature of the MIRI must not exceed 6K, which is maintained by a helium gas mechanical cooler located on the heated side of the environmental shield. The Canadian Space Agency's FGS NIRIS, which is the abbreviation of Fine Guidance Sensor, a near-infrared imager and slitless spectrograph project, is led by project scientist John Hutchings of Hesburgh Astronomy and Astrophysics Research Center, National Research Council, is used to stabilize the observatory's line of sight during science observations. The FGS provides data that's utilized to regulate the spacecraft's general orientation and drive the fine steering mirror for picture stabilization. The near-infrared imager and slitless spectrograph module, directed by René Doyon of the Université de Montréal, is also provided by the Canadian Space Agency for astronomical imaging and spectroscopy in the 0.8 to 5 meter wavelength range. The NIRIS and the FGS are commonly referred to as a single unit since they're physically installed together. Nevertheless, they serve entirely different objectives, with one serving as a scientific instrument and the other as part of the observatory support infrastructure. It's fascinating to know how many minds and how much technology is used in constructing this epic machine. Once we get to see the images from this amazing thing, we'll be able to understand our universe a little better.